chain rule, I think that it's easier to just practice and understand it that way, but everyone is different. So it might help to have these definitions as you're working through. So let's do some examples so we can see what this is actually saying. So I'm just going to write that definition on the side here. So we have our original function is x, and it is a composition of e of I of x. And the chain rule says, I'm just rewriting the chain rule over here, the derivative of f is the derivative of e times the derivative of I. So we're not going to fully separate the two layers like we did in the previous examples, but we should be able to see from that practice what our two layers of function are. So E, the exterior in this case, is just the part that's happening on the outside. So it's this thing raised to the fourth power. Our interior is the part on the inside. So that's the 3x plus 1. So the chain rule in words is the derivative of the outside times the derivative of the inside. Or if I'm using the book's words, the derivative of the exterior times the derivative of the interior. So if we're looking at just the exterior part, we have something raised to the fourth power.
X.
Yes. And so we're not going to rewrite it as x just yet, but we can think of it as just like if this was an x to the fourth power.
That'd be 4x to the third.
Right, exactly. So our power rule would say, take that power down and lower the power by 1. The weird part is that this isn't just x anymore, it is everything that was in there. So this part is the derivative of the exterior. That's that E prime part. That's why in our chain rule, that I to the x, or I of x is still in there because we're not actually changing the interior. The interior stays the same. But then we're going to multiply by the derivative of the interior.
3.
Exactly. So I of x was just that inside part, 3x plus 1, and that is just 3.
That's pretty cool.
Yes, there's a lot going on here. So the chain rule says we do the derivative of the exterior times the derivative of the interior. It has always worked better for my brain to just remember that rather than remembering the sort of formula definition of the chain rule.
You may have said this and I may have missed it, but are you going to be giving us this equation on the test as well?
I didn't say that, and I was just thinking that no, I won't be. The chain rule you should know. So you will get the product rule and the quotient rule and the general exponential and logarithmic rules, but not the chain rule. And not the natural exponential or natural log. And I will tell you that formally soon, what exactly I'll give you on the test and what I won't. But the chain rule will not be given. You'll have to know it.
Thank you.
Are all the chain rules kind of similar to this setup, or do they start to get fractions and square roots and other things in them as well?
They get other things in them. Yes. But we're starting with some power rule things, or some, yeah. And we do have one little last bit to do here, which is that we should simplify this. We have that 3 multiplied at the end, which can multiply with the 4. So we really should get 12. 3x plus 1 cubed. So the chain rule is all about these layers of function. We just start on the outside and see if we're walking towards this function, what part would we hit first? And in that case, it's the cube. So we are using the power rule to take the derivative of the cubed thing, or excuse me, the 4th power. I'm looking at the derivative. The first thing we hit is the 4th power. So we use the power rule to bring that 4 down and lower the power by 1. The inside stays the same when we do that. Then in our next step, we're now on the inside of the function, and we can do the derivative of that inside. So let's do another one. So looking at this function, we have y equals x cubed minus 5, all raised to the 5th power. So if we're peeling off that first layer, the first layer is the something raised to the 5th power.
5 to the 4th power.
Right,
It's
exactly.
going to be the outside.
Right. So the derivative of the exterior is just using the power rule to bring that 5 down and lower the power by 1. The inside part is staying exactly the same for now.
And times 3x squared.
Right, exactly. The derivative of the interior.
Then would that be 15x squared?
Yes.
And then x to the 3rd minus 5 to the 4th?
Right, exactly.
Perfect.
Before I write that, I'm just going to make this little note again. I probably won't write this on every one, but just so we see it. We did the derivative of the exterior part first, which was just the power rule, and then we have the derivative of the interior. Once we have those two pieces, see, there are the fractions and radicals that were mentioned before. So once we have those two pieces, we should simplify. So it's weird to have that little 3x squared just floating on its own in the back. So we can multiply the 5 and the 3. And in general, we would write that x squared first. There's absolutely no reason to FOIL out that x cubed minus 5 to the 4th. So please don't, unless you just want something fun to do for yourself. We'll just leave it as it is. Okay, let's build on this. And this should definitely be a t. Can't take the derivative with respect to x if there's no x. There we go. So before, oh.
No, it just looks gross.
So before we tackle this one, I just want to make a little side note. If we were doing d dx of 1 over x squared, this is something we were doing in chapter 2, 1 over x squared. How would we first rewrite this so that we could use the power rule on it?
X to the negative 2.
Yes, exactly, x to the negative 2. So when we first see 1 over t squared plus 4 squared, it probably looks like a mess. But if we think of it in terms of this chain rule, we can think, oh, this is just 1 over something squared. So we can rewrite it as that something to the negative 2. So now we have a power rule. So this is going to be d dt of, I'm just adding some parentheses here, t squared plus 4 to the negative 2. That parenthesis was unnecessary. So all of the rules we have are what we're using here. So this is, even though it's starting out looking a little bit nasty, we can think back, and when we're looking at our interior and exterior, we can recognize that this exterior of 1 over something squared is really just x to the negative 2, which gives us a way to use the power rule. So now we're doing the chain rule. So d dt means take the derivative of what's following. So right now we have something raised to the negative 2. So that something is going to stay the same.
And negative 2 and negative 3.
Right, exactly. So the negative 2 comes down and multiplies, and then we subtract 1 from the power.
And times 2t.
Times 2t, exactly. So we did the derivative of the exterior, and now we have the derivative of the interior. And this, we can do the same kind of simplifying as before, which will be to multiply the 2 and negative 2 and just bring that t out in front. And that would be acceptable as it's written. We could also move this back to the denominator. So let's do one more that's using the power rule, and then we'll build and use some of our other rules as well. So before even taking the derivative here, we should think, oh, we have this square root on the outside. The only way we know how to take the derivative of a square root is to change it to a power and use the power rule. So we should do that. So all of the work we did with rewriting things in a way that we can use the power rule on them still applies to the chain rule. So we see this square root and we need that to be in its power exponential form. So now our exterior again is a power. This thing raised to the 1/2.
It'll be 1/2,
Mhm.
and then 4 minus W, so the negative 1/2.
Right, exactly. So we're taking that power down to the front and subtracting 1 from the original power. The 4 minus W stays just as it is. But then we have to multiply by the derivative of the interior.
Which is negative 1.
Right, it is just negative 1. And so that negative 1 can multiply with the 1/2, so it gives us negative 1/2. And this would be a fine answer. We could also get that power to be positive, oops, by bringing that 4 minus W down. Or we could change it back into its radical form. So the focus definitely right now is on the chain rule. So as long as we get the chain rule bit right, that's the important part, but both of these are also correct. Just like we did before.
It's weird how they're so different, but yet the same.
Mm-hmm. Yeah, they do look very different. So far, all of these have used the power rule as their exterior function in different ways. So we have the radical, which still uses the power rule when we change it to 1/2. And even if it was in the denominator originally, we changed that to a negative power. All of these have been using the power rule as their exterior and interior, I guess, yeah. But we know other rules as well. So more chain rule. Here we have our function is e to the 4x. exponentials are often one of the hardest for people to see the interior and exterior to begin with, because we don't have those same sort of like nested parenthesis type things. But as a general rule, and actually this will always be true, if there's something other than just x in the exponent, like there is here, 4x, the exponent itself is the interior. I can spell that would help. Exponent. So we have our exterior function, which is e raised to a power. We know the derivative of e to a power. Then our interior is that power itself, the exponent up there. So our exterior is e raised to something. What is the derivative of e raised to a power?
The same?
The same, exactly. So no matter what that power is, e raised to a power is just itself. So this little bit so far is that derivative of the exterior. Derivative of the exterior. It doesn't change because it's an e to a power. Then we still have to multiply by the derivative of the interior.
Which is the same?
Not quite. So the
It's
interior.
4.
Yes, exactly. Just 4. The interior is that 4x, the exponent up there. So the derivative of 4x is just that 4. Having trouble writing derivative today. Derivative. So when we're working with the chain rule, when we see an exponential, we should think that that power, the exponent itself, is our interior function, whereas the whole exponential expression is the exterior.
So whatever number is paired in an e base x power would be the interior number?
Whatever the power is, so this isn't necessarily going to be just a number times x. It could be some other stuff. It'll be just whatever is in the exponent will be the interior.
Okay, so why is x not part of that then?
So the interior itself is 4x. 4 is the derivative of the interior.
Ah, gotcha. Okay.
And just because it's kind of weird to have a 4 multiplied to the end, it is more simple to bring the 4 out front. Let's do another exponent one.
Just real quick, Madeline. It may help with some people. It helped me with just like doing what we did with the last equations, where you did the, I guess, and those would be the b of t and then the derivative of b and t. I did those all on the side and then I put them all together. I don't know if it would help. It sounded like it would help her. Does it help me?
So like on this one saying that like E for exterior would be E to the X. And E prime is itself. I in this case is 4x. And I prime is 4.
Okay. Yeah. Thank you, Corey. That helps.
Yeah, no problem. It helped me out a lot.
Okay, I'll do that for the next ones.
Yeah, I actually did that too.
I do, the only, my only concern is on this part. So we have to make sure that when we put it back into the actual derivative, that exponent is being turned back into its original exponent. So we just have to be careful about that.
So why does it go back to the original exponent?
So because our chain rule always keeps the interior as itself when we're working with the exterior. So if we go back to our chain rule, the E prime, when we do the derivative of the exterior, that interior is staying exactly the same inside that exterior derivative. It's not until we get to the interior derivative that it changes. So here, when we were doing our derivative of exterior and derivative of interior, when we do the derivative of the exterior, which was the power rule in this case, that interior part stays exactly the same. That didn't change. And then we do the derivative of the interior. And this is exactly why I don't usually write it in this way, and it's totally fine if it helps you to write it in this way. But we need to be careful. So I would actually, let me erase a little bit of what I've written here. Really what's happening here is that this is E of 4x. So our exterior function is the whole e to the 4x. But when we do the derivative of e of 4x, we're taking the derivative with that interior function still in it. So when we're working with the exterior, the interior is not changing at all, ever.
So it's like the other rule, but not really like the other rule.
No. It is not like the product and quotient rules. It's not, yeah, it's not. The chain rule is very much its own thing. And so, and the other definition of chain rule, and it might help also, where did it go here? Is to replace the interior with u at first. So this is another way to write the chain rule, which is instead of writing E, let me move this out of the way for a second. Is to write the exterior with a U in it as just sort of a placeholder. And so if our exterior function is E to the U, then the derivative of our exterior is also E to the U. And u is just whatever happens to be in that function, which is 4x in this case.
Okay.
This is why I don't like writing the actual definition of the chain rule, because there's a lot of parts that are really easy to confuse.
Again, Madeline, just to add on to that, what I also did was put out the whole equation, so I reminded myself. So like the derivative of f of x equals e of I of x times the derivative of I of x. And then I just kind of filled it in after that.
So after doing, did you write it E and I like this? So we can write those exterior and interior and exterior derivative and interior derivative like this. And then we can use that definition of the chain rule like this and plug everything back in.
Yep, that's exactly how I did it.
Yes, so you also can do that. So our E prime is E to the X, but now we're putting I back in there, which would be 4x times I prime, which is 4. And you can't do that. So this is as long as you are doing the chain rule correctly, any of these ways is acceptable. So if it works for you to find this E prime, I prime, and then fit them all exactly back into the formula, that is great. And you can do that. If it works for you to replace I with U and use that as your when you're doing the exterior part, that's also fine. If it works to just go and sort of work in these layers of doing the derivative of the exterior and then the derivative of the interior, that also works. So I will be checking your work to make sure that you're showing your work and doing it correctly, but I won't be looking for an exact way as long as it's done correctly, the derivative of the exterior and the derivative of the interior. So we are out of time, so we're gonna continue practicing the chain rule at the beginning of class on Thursday, and then we're gonna do section 3.6. So we're gonna skip 3.5. That's the plan. So I will see you then. Have a good couple days.
Thank you, Madeline. Have a great day.
You too.
Do you
Thank
have
you.
class hours today?
What was that?
Do you have office hours today?
Yes, drop in 1:30 to 2, and then I have by appointment between 2 and 3.
Can I get in about